So a brief overview of the talk. We will firstly discuss why feature importance measures are important, as of course we first need to ensure that what we are talking about is relevant to a data scientist. We will then go on over a brief historical overview of a few feature importance measures, and we will look at the disadvantages as well as some advantages of those historical ideas. We'll then concentrate on the Shapley value-based feature importance measures, and we'll overview both caveats of how to use them and their theoretical mathematical basis, which I think is quite important to understand in order to really appreciate how Shapley value-based feature importance measures shine. And then we will just summarize and have the break. So let's start. Why should we care about feature importance at all? Well, machine learning gets more and more automated. So we have automated feature engineering, we have deep learning models, tree ensembles, which can capture quite complex relationships between our target variables and our data. So human input becomes less and less relevant. This sort of automation also reduces the time to production of our models, so that we can utilize data quicker and thus ensure that the company sees the results faster. Well, but nonetheless, model criticism is an important issue. There are multiple reasons why we may want to probe the reasons why a model makes a particular decision, and just ensure that it makes the right decisions. So first of all, we may not have a complete understanding or a complete formalization of the phenomena that we aim to model. Secondly, there may be data that incompletely describes the phenomenon. So even if we have access to all the data that we can, given the circumstances, it may still not fully describe the phenomena that we aim to model, which is sometimes quite relevant in various business applications such as marketing or credit. We also may observe changes in the phenomena or the population that we model over time. So even though we have had a very accurate model which made the right decisions for the right reasons at the outset, there may be a population shift that makes our model less applicable once we deploy it to production and run for a while. And finally, there are certain factors that are completely external to the phenomena that we model that may still influence them. We may not capture these phenomena in our model, even if we have a full understanding and full data. This is particularly acute in credit risk. So in credit risk, we don't have any explicit causal model of why a loan or a credit card defaults, that is, misses payments. We also have only access to data that describes a small part of the phenomena. So particularly, we usually look at historical credit data, but there are multiple other factors such as economic data or demographic data that we just don't look at. So while we try to get use of all of the data that we can to make the best decision, it's still a small fraction of all of the data that actually drives credit risk. Also, it is evident that credit risk factors change over time. So specifically, particular credit products may give rise to particular new features that may not existed in the past. A good example here would be payday loans. As you know, payday loans are now somewhat in decline, but they used to be a pretty big factor in someone's credit history. And finally, we just want to be able to explain why our model, we also may want to explain our model to regulators. So regulators may not necessarily be the most technical people who are keen to study deep learning. to understand how our model makes decisions. They want to understand, by reviewing certain cases, that the model made the right decisions. So this stress between accuracy and automation and interpretability gives rise to a new phenomenon that I'll try to describe right now. Specifically, because we now have such high levels of automation, we can ensure low time to production if we sacrifice some of the interpretability of the model. We can just run it through automated feature engineering pipelines or some of the tools that offer automated model construction. However, if we want to, at the same time, also have high interpretability of the model and understand why it makes decisions, it may require more data scientists' time and effort. So we may need to ensure that we are using non-collinear features in some trivially interpretable models, such as logistic regression. And that simply is difficult to achieve and requires a lot of time and effort. Is there a way to combat this accuracy-interpretability trade-off that is now arising in the industry? Well, there are actually a few ways. So we can limit the class of models that we are interested in to only interpretable models, such as a logistic regression or linear regression, and automate feature engineering in such a way that ensures that we capture most of the complexities in the data. We can also use a wider array of models to ensure better accuracy in the end, and use some model-agnostic or black box model interpretability methods. Specifically, we can probe feature importances, among other things, and look at which features are the most important using some of these methods that I'll talk about. This allows us to quickly build models and also be able to inspect them so that we can explain why the models are making the decisions that they're making. So let's start from some historical feature importance metrics. And let's look at some of the probably simplest one that you could use, which I assume a lot of you have already had a chance to use, as it is bundled together with a lot of data science packages, as well as cloud data science environments. And that's permutation feature importance. So what happens when we are applying permutation feature importance? Well, we're taking some data, be it our training or validation data, and we are iterating through features, feature by feature. We are then permuting each of the features so that we break any link between them and the target, while at the same time not changing the feature distribution. We then evaluate the model on the new set and look at how much the metric of our interest changed. So let's say we have a simple model. We just permute one of the features. We rescore our data set with the new model. We compute our metric. Yeah, so in the end, we just evaluate the metric of our interest, be it ROC-AUC, R squared, whatever we're interested in, and look at the delta. That's it. It is quite simple to understand, and it can also give useful insight into which features really drive the model's performance. But let's assess it in more detail, and let's see what it actually does. One of the key things that we probably want from a feature importance measure is for it to take into account possible feature interactions. And here, because we permute each feature independently of the others, this is not taken into account. So effectively, permutation feature importance can only give faithful measures for models where features are fairly independent. Now, secondly, we can only probe feature importance on a population, on a big data set. So we cannot really explain individual decisions that the model has made, which makes this particular method less applicable in situations such as credit risk, where we may want to explain why a particular customer was given a particular loan application decision. it is also the case that because we are using a particular data set to compute our deltas and our metrics from which we compute the deltas, the importance measure depends on a population assumption. So feature importances that have been computed would no longer be valid in presence of population shifts. So let's say if we want to monitor our credit risk models and there is a big economic shift in the country, then we could no longer be able to validly use our permutation feature importances. But what is very good about permutation feature importance is that it does very neatly and succinctly summarize models' actions, models' decisions. This can be useful if we indeed have a simple model or just want to quite quickly probe why the model is making most of its decisions or what drives models' decisions on average. So let's try to look at something that is slightly more complicated, and namely partial dependence plots. So before that, I'll make a few mathematical definitions. And I'll try to keep mathematical definitions quite brief and simple. But in order to really explain the theory behind Shapley values that I'll go on to explain later, I think we will need to go into mathematics to some detail. So let's just define a feature space. We can consider a feature space as basically just a subset of some vector space. Effectively, as we can see in this image, in this heat diagram, heat map, some of the points in our space will be more likely to be observed than others. So we effectively have a distribution assigned to some vectors which defines our population. And we can think of the feature space as that. A brief note is that for purposes of mathematical consistency, I'll also assume that feature spaces are actually finite subsets of the real vector space. So we have a feature space, and we can cut it. So effectively, we can look along each of the dimensions. And here specifically, we could look at, as you can see in the picture, we can look at the x-axis along this heat map. And we can just pick a particular strip along that axis. That would correspond to a specific value of the feature represented here by the x-axis. And we can just look at this cut. And you can see the mathematical notation for these types of cuts on the screen. And investigate it. So let's say that we have a model, just a simple function, which let's say, for simplicity, let's just consider classifiers, although this is equally applicable to regression as well. We just have a function which maps to some value between 0 and 1. We can look at what's the expectation of the model's output over a particular strip. And so if we actually plot these expectations strip by strip for a particular feature, so for all the values, all the possible strips along the x-axis, we can end up with something that is the partial dependence plot. It will show us how the average or expected value of the model changes when we change a particular value of a particular feature. And it can be quite informative. It can definitely show us where there are any significant shifts, where a particular feature represents a big drop or a big increase in the model score. That is very useful to look at. But let's assess it in a bit more detail. And let's assess it according to the same criteria that we have used before. So are we accounting for feature interactions here? Well, not really, because we are plotting each feature independently. So while we can potentially, by applying further analysis, find out that particular features do interact because they change, their expected values change at approximately the same points, we, however, cannot immediately see that in a succinct way from partial dependence plots. Can we explain individual outcomes? Could we explain why a particular credit application has been declined, for example? Well, again, probably not. although we can indeed use these plots to infer particular edge cases here and there, and we can, by applying logic and further statistical analysis, indeed find out why a particular thing has happened. In some cases, there is no theoretical guarantee that this will always happen, and it does require human effort. And as before, we do depend on our population assumptions. So in presence of population shifts, because we did sample from the feature space to compute the expected values of the model, our partial dependence plots may no longer be valid. Well, and finally, is a plot for each feature, where we may have 40, 50 or so features, really a succinct way to summarize a lot of complex information? Probably not. We can use them definitely, and it can definitely be quite insightful, but it is not something that can be used, just be a readily made application in the business for everyone to understand how the model behaves. And that's why we have to come to something more complex. So let's start talking about Shapley values. And for that, first, let's review a few concepts from game theory. So let's consider a collision-form game. Let's start by an example. Let's imagine that there is a company and it has a number of employees. And the company, together with the employees, generates some number of pounds, some profit. We want to then take that profit and somehow attribute it to the firm, which would mean the institution, shareholders, as well as each individual employee. How could we potentially do that? Well, having considered an example of a collision-form game, we can now think about a mathematical definition of it. So each collision-form game mathematically is defined as a tuple of a set of players and a worth assignment function. The worth is assigned to each collision of the players. So each possible collision that the players could form, let's say 3 employees together with a firm or 2 employees without a firm in the previous example, are each assigned a particular worth, which would be some amount of pounds in that particular example. In that particular example, for example, any employee collision without the firm in it would be worth 0 by the definition of the game. We usually assume when we are dealing with collision-form games that a grand collision, that is, a collision of all players, is formed. It has a particular worth, and we are considering how to redistribute that worth to individuals. And not only how to redistribute that worth to individuals, but also how to redistribute it in a fair way. So, as we can see here, we want the total profit, that is the worth of the grand collision, to be split into parts which are not equal, but which somehow reflect the credit of each particular player. And mathematically, we talk about a particular function phi, which represents that. Shapley's contribution are a set of 4 axioms which encapsulate what he considered to be fairness. And these are indeed quite agreeable axioms. So let's briefly go through them. First of all, we have the efficiency axiom, which just requires the total worth of the grand collision, that is the total profit, to be fully redistributed. So we just want our individual slices of the pie to sum up to the whole pie. There's also the symmetry axiom, which in intuitive terms just says that 2 players who contributed in exactly the same way should get the same amount in the end, if we are redistributing fairly. There's the dummy axiom, which is somewhat similar, and it just says that if a player has not contributed, that is, any collision where the player participated was worth the same as a collision without that player, then the player should not get anything. And finally, we have additivity axiom, which in intuitive terms, it would just mean that if we have two different games, so let's say two different companies, and they may share employees, the total amount that employees are rewarded should just be the sum of their rewards from the individual companies. These four axioms seem to be fairly intuitive, and it is hard to see how we could think of fairness without agreeing to them. But what is surprising is that if we assume these four axioms about our redistribution function phi, then there is only unique such function for each collision form game. And effectively, the values that each player gets, the redistribution of the worth of the ground collision that is attributed to each player in the end, are called Shapley values. How is this related to machine learning? Well, we can start by just a thought that we can think of a feature importance as a stake in the model prediction, overall model predictions value. This is intuitive if we think about it in terms of, for example, a logistic regression. There, the sum, there the final logit, that is the log odds of the probability that is predicted, is just a linear sum of the contributions of different values and some baseline. So we can potentially think of each feature as contributing a particular bit to the model prediction value. Well, to formalize this notion, we can think of prediction difference. So for any fixed set of feature values, we can look at the prediction difference of the expected, the model expected value when those features are fixed versus the overall average value over all feature space. So if you think and remind yourself about the partial dependence plots, where we were plotting the values of the expected values of the model score along each strip, along each axis, here we're doing something very similar, except we're also subtracting the average model score over all feature space, which we can think of as our bias constant effectively. And in order to be sure that we are really taking into account all feature interactions, let's define implicitly our prediction difference for a particular fixed set of features as a sum over all interactions in that particular set. And then consider a function phi, which just assigns to each feature the total sum of interactions that feature participates in, weighted by the size of the feature coalition. We are effectively just summing over all interactions that the feature participates in and weighing them. And what is surprising is that this particular function, that is the prediction difference, together with the set of features for a model, prediction difference being fixed at each particular data point, actually defines a collision form game. And the value that we were talking about, the weighted sum over all interactions that the feature participates in, is effectively its Shapley value. So here we have a way to redistribute the full model score to each individual feature in a way that uniquely that is unique given a set of axioms, which, if we consider, are very agreeable and also are very directly applicable in a context of a classification or a regression model. I will not have time to do that right now, but if you have time after the presentation, you can go through the four axioms and really think of whether a classification or regression model could not be subject to either one of them. So, having defined what Shapley value feature importances are, we can then look at some of the useful properties of them. So, First of all, we can express the model score at a given data point as a sum of feature contributions and a bias term, let's say. This means that we can use traditional logistic regression-based representation of a model's decision for any classifier or regressor. We can just represent each model score as a sum over components of different importance. This is quite intuitive, especially in the credit scoring space, where traditional credit scoring models are logistic regression models. People do not necessarily need to adapt or think too deeply about how a particular model is different. They can just use some of their current workflows to monitor and understand these models. This gives us interesting ways to monitor the model and to see if there are any shifts. So let's say that we have such a representation of features contributions, as discussed before. Here, the top picture shows it horizontally. But what if we actually rotate it 90 degrees and then stack these feature importances as a sort of area chart, one next to the other? Well, this starts to highlight certain shifts in our population, as we can see. Finally, what is worth mentioning about Shapley value feature importance measure is that it is related quite deeply mathematically to some other popular individual model decision explanation methods. So specifically, if we look at something like LIME, which I won't go into detail explaining it, but if we look at something like LIME, what we will actually observe is that Shapley values are a particular kernel and a particular model in the more general LIME model space, which also has some additional theoretic guarantees. So we can really view Shapley values not as a competitor to LIME or some other similar feature explanation, feature importance measure techniques, but rather as a way to unify it and to really give it deep mathematical grounding. We also have numerous very fast algorithms to compute Shapley values. Specifically for tree ensembles, there is something quite fast. But we can also approximate Shapley values by using sampling over our feature space. And all of it is already implemented and readily available in the Shap package online. So to move towards the end, let's just summarize the caveats and the advantages of using Shapley values. Well, first of all, we have to understand that Shapley values still depend on the assumption of the population. So we are still having an assumption of the feature space present. And if there are significant shifts in our population to which we apply our models, Shapley value-based explanations would still not quite be valid. However, we can always monitor whether there are any population shifts using standard statistical tests or just plotting our population time after time. It's also worth understanding that because of the way it's defined, Shapley values in presence of two identical features will distribute importance to both of them equally. So if we have two ideally predictive features, each of them will only get half of the full performance. This stems quite directly from the axioms, and specifically, if we think about the symmetry axiom, similarly, well, identically behaving features should be scored identically, but it is not necessarily too intuitive in all cases, because usually when we're thinking of feature importance in, for example, feature selection, we only want to have one feature that is important in a set of features that are very similar. We have to understand that Shapley values will just redistribute this importance. And if we have a highly collinear set of features, the Shapley value results would not necessarily be too intuitive if we are used to non-collinear independent sets of features. So for the final assessment, we have very explicitly accounted for feature interactions, as Shapley values are nothing but the sum of feature contributions towards the model score across all possible feature subsets. We can explain individual outcomes because we are looking at each individual data point separately, and the prediction difference is a function defined and dependent on the specific data point that we are looking at. We are still depending on an assumption of the feature space, or our population, as just discussed. And finally, we have a way to summarize feature importances in a very traditional, readily readable way. So it seems that Shapley value importances are indeed quite a promising way of probing black box models. And let's end with that, just summarizing what we have discussed today. So we have looked at a few traditional feature importance probing techniques, specifically permutation feature importance and partial dependence plots, and we have seen that there is one core issue with them, and that is that they don't really probe feature interactions. We have then looked at Shapley values, which do. But we have also noted that there are some caveats around the use of Shapley values, specifically when we have a highly collinear set of features. We should be aware that the feature contribution to the model will be redistributed for very similar features to all of them equally. And finally, I would just like to point out that while we have discussed a lot about how to probe black box models using various specifically designed techniques, there is also that opportunity to construct an interpretable model from the outset. And there are some promising methods to build complex features which can go directly into something like a linear or logistic regression automatically. This is another path that's worth exploring if you really care about model interpretability, but well, it was simply not the focus of this talk. I think that's it.